All right, now what I'm going to do is I'm going to show you how to make a unit vector. Unit vector in the same direction as our vector v. Now, what is a unit vector? What do we know about unit when I hear about the unit circle or the unit value? It means the unit vector is typically denoted by u, and if it is the unit vector, it implies that its magnitude is always 1. Okay, that's what a unit vector is. So how do I take a vector v and I shrink it down? So basically what I'm wanting to do is I'm wanting to take some vector v, right? Let's just keep it in the first quadrant to keep it simple. Okay, and we're going to call this AB. And what I want to do is I want to shrink this thing down, but I want to maintain the angle. All right, I want to maintain the direction. So if you think about it, if this is theta when we start, I want that to be theta when we're done. The only difference is I want this length to be 1. So I want this thing to be a unit. Okay, with me? It's actually really, really simple. Watch, I'll show you how. If I want a unit vector in exactly the same direction as v, all I do is I multiply it through by a scalar. And the scalar that I multiply it through by is actually the magnitude of v. Remember, magnitude of v in this case is root a squared plus b squared, just fancy old Pythagorean theorem, right? So if I want to turn v into a unit vector, now I'm going to change notation. I'm going to go from, I'm going to call this ai plus bj, okay? Then what I do is I take a, and I divide it through by the square root of a squared plus b squared, right? So I'm just think of that as multiplying through by a scalar, plus b divided by the square root of a squared plus b squared j. Now, there's a proof here. If you think about it, what I've done is if I multiply through by a scalar, that angle is always preserved, right? I've just scaled a and b back. A shrinks back in this case, and b shrinks down until we get to this point right here. But I do have to prove that the length of this is 1. I don't have to worry about the angle because I know if I multiply, in other words, if I shrink them by the same amount, then I end up with the same angle. I've changed nothing. So let's prove it. What is the magnitude? What is the magnitude of u? Well, isn't it just this guy squared plus this guy squared, the square root of that? Well, so I got a squared over a squared plus b squared, right? Plus b squared over a squared plus b squared. I'm just squaring these terms. The square root of this, which is the square root of a squared plus b squared over a squared plus b squared, which, you guessed it, is 1. All right, now, so what we have is we have a general formula. I can take I can turn any vector into a unit vector simply by taking the vector and dividing it through by the magnitude, which really, again, I want you to think about this. It's not just dividing through by the magnitude, but it's really multiplying by a scalar. Remember, magnitudes are numbers. They're scalars. They're not vectors in and of themselves. But algebraically speaking, isn't this true if and only if v is equal to the magnitude of v times the unit vector, right? I mean, there's nothing fancy there. Now, that's pretty simple, right? That's just algebra. That's kind of a cool way of thinking about it. In other words, if I know that I have a unit vector in the same direction as v, and then I multiply through by the magnitude, then I can get exactly the same vector. I haven't lost anything. Now, I'm going to do something that's going to make it's going to look like voodoo. All right, but I think you'll like it. It's pretty cool. It's a fun way. It's a really cool way to describe vectors, and it's really going to help us with our static equilibrium problem, which we're going to discuss in class. Now, check this out. Let's make a vector. We're going to give it. I'm just going to call this vector A, B, and I'm going to give it an angle measure. Okay, I'm going to call this theta. Now, there's no assumption that v is a unit vector, and in fact, let's assume that it isn't. Now, let's think about something for just a sec. I'm going to rewrite this type, see what we did up here? I'm going to rewrite this unit vector using sort of a clever trigonometric trick. Do you guys agree that if I take the unit circle, all right, remember x squared plus y squared equals 1. Then this length right here, let me change my colors real quick, then the length right here of this guy has absolutely no choice but to be 1, right? It's on the unit circle and it's centered at the origin. So think about that. As soon as I'm on the unit circle, what can I say about these sides? Well, I know that this side, the x, remember this point right here is going to be x comma y, right? But we are going to turn this into a vector, but just bear with me for a sec. If this is x comma y, then isn't x just, x is going to be equal to cosine of theta, right? And y is going to equal sine of theta, correct? So can I think of this as being the magnitude of v times, now remember, these are horizontal and horizontal and vertical components of this vector that I'm trying to make. Well, watch this. It's pretty cool. The horizontal component is cosine of theta. Now, times I, but I don't want to put the I on the right because I might think that I is the square root of -1 or something crazy. Remember, it's just a marker. It just tells us in the physics sense of things, it tells us that it's the horizontal component. I'm going to put it here. I'm going to write it as I cos theta plus J sine of theta. That's pretty cool. That's really cool, isn't it? So you can take, if I can figure out what this theta is, if I want to rewrite my vector anytime I want, I can simply take it as the magnitude of the vector times I cos of theta plus j sine of theta. So you'll see this written like in your textbook as cosine of theta I plus sine of theta j. It doesn't matter because the commutative property of multiplication tells us we can write it however we'd want. In the book also they make this I bold. Then they make this j bold. And the reason they do that is because they don't want you thinking this I is not equal to the square root of -1 in this context. Okay? Now, that's pretty cool. Let's do it. Let's just do it real quick. We're almost done. I'm going to talk a little bit about static equilibrium, and then we're going to do a whole bunch of static equilibrium problems in class. Okay? Excuse me. Let's do one of these. Let's take the vector. I don't know. Let's go 3, let's make it better than that. Let's go 3, 6. 3, 6. Okay? It's a vector right here. And I want to write it in this form. This is the form that I want to write it in, this guy right here. Now think about what we got here. This won't take very long. I go over 3, 1, 2, 3, up 1, 2, 3, 4, 5, 6, right? So that guy right there, and this is 3, 6. That's that vector. Now all that I have to do is figure out what theta is. Well, hopefully already your spider sense is starting to tingle, right? If this is 3 and this is 6, what do you notice here? What's that? What do you notice? You notice that the tangent of theta is equal to what? 6/3, which is equal to 2. So theta equals the inverse tangent of 2. Now, you know what? I forgot to pop up my calculator, so I'll just cheat here real quick. I'm going to put my mode in degrees, just so we can see what we're talking about here. And I'm going to go second inverse tan of, I know that's cheesy for me not to have a calculator, but that's all right. So theta is approximately equal to 63.4 degrees, which means that if I can figure out what the magnitude is, well, how hard is it to figure out what the magnitude is? Well, I'm going to have to come over here. Sorry, you guys. I know that, what did I say? V equals 3, 6, right? We know that tan of theta equals 2, so theta equals the inverse tan of 2, which is equal to 63.4 degrees. I know that the magnitude of V is equal to the square root of 3 squared plus 6 squared, right? Which is what? Square root of 45? Which is 3 root 5. So I can rewrite V as 3 root 5, the magnitude of V, times what? Cosine of 63.4 degrees times I, put a little degree in there, plus J times the sine of 63.4 degrees. I can rewrite that. Now you may say, really, wait, why are we overcomplicating this? Trust me, it'll help us hugely down the road for us to be able to do this. All right, now one last thing and then I'm done. I know it's been a long lecture. All right, but one last thing. Let's talk about static equilibrium. Static equilibrium. Static equilibrium simply means that you'll have a system of vectors wherein nothing is moving. In other words, all of the vectors balance out. So like the simplest case is a tug of war. Let's say that somebody's pulling this way with 50 newtons. If I want this thing to be in static equilibrium, I need to pull this way with 50 newtons. Now, if we think of these as being vectors, I mean, think about that. What would that have to be? Well, if I'm going to call this V and I'm going to call this W, then V would have to be what? It would have to be 0I plus 50J. Remember, think of this as being on the coordinate plane. What would W have to be? It would have to be 0I minus 50J. Notice, if I add V plus W, I get 0. So static equilibrium implies that the sum of all vectors is equal to 0. It means it's not moving, right? That makes sense? Now, if these numbers were different, let's say that this was 2I plus 50j, well, then I'd have a different looking vector, wouldn't I? I'd have a vector, let's see, 2I plus 50j. I'd end up with something that was like shooting up this way, right? Which means I would have to apply the same force in the opposite direction, and they would have to cancel. All right? Okay. Well, we're going to play with this a whole bunch in class. I just wanted to give you the vocab. I wanted to give you a couple of definitions, and I definitely wanted to give you this equation, these two equations. Probably these two equations right here, and then this guy right here, which turns into this guy, are the most important. They really are, other than, of course, like being able to figure out the magnitude of the vector. So, important stuff. I'll see you in class tomorrow. We're going to work pretty heavily on vectors for the next couple of days. All right? Have a great day. I'll see you.